Right, good afternoon, everybody. I can see that at this point in the schedule, everybody has identified their chair. Like, right, there's one place that is just your place for this class. You might want to try changing perspectives a little bit, right? What is lecture like if the letters are smaller or bigger, right? Or if the aspect ratio is different, does it make it more exciting, right? We've been talking about relaxation, very important topic at MIT. I finished up last time talking about the vertex cover problem. And after class, somebody asked me a question that they really should have asked in class, as I've said before, right? Your questions often point at things that are really interesting that it would be valuable for the entire class to hear. And in fact, I wanted to make a very concrete point, which is that sometimes in this class, I get so excited about the material that I forget to look at the lecture notes and skip entirely over some important point. And your questions will often remind me of these important points that I skipped over and allow me to make them. So please keep the questions coming. This is a question about vertex cover. And the tightness of the relaxation. If you remember, we talked about this simple LP relaxation, which was based on this so-called stable set polytope. Which is defined by these constraints that xi plus xj is greater than or equal to 1. Or actually, the stable set polytope is for the complementary problem. And so it goes the other way around, right? The stable set is a synonym for independent set. And so the LP relaxation for independent set uses less than or equal to 1. But for vertex cover, we want the complement at greater than or equal to 1, right? And we showed a 2 approximation based on literally rounding the xi's, right? And I talked to you about the hardness results that and actually I have some, I can fill in a little bit more detail on this, that at this point we know that root 2 is hard. You can't beat square root of 2 unless p equals np. And this is from 2017. There was a series of results that raised the hardness higher and higher. But there still is a gap. And I also mentioned that it's too hard if the unique games conjecture holds. But something that I failed to mention last time, which is also really interesting, is the relationship of this stable set polytope to the 2 approximations. So we have this rounding that gives a factor of 2, and somebody came down and asked if it's tight for this relaxation, right? So there's the question of hardness, which is a harder question, but you can also just ask if this particular relaxation is able to beat a factor of 2. Right? So when you have an LP relaxation, it's interesting to talk about the integrality gap, which is the gap between the fractional and integral optima of the LP. Okay. So I claim if the integrality gap is, say, 3, then you cannot hope to approximate better than a factor of 3 in your problem. People see why that is? Or rather, I should say, you cannot hope to approximate better than a factor of 3 using a rounding of this linear program. Yes?
You can only round the rational to the nearest integer?
Exactly. I mean, the point is that when you round, you're going to get an integer solution. And so, you know, if you have a solution that is fractional, but is off by a factor of 3 from the best integral solution, then when you round it, you're going to be off by a factor of 3 from your original fractional solution, right? And the way we analyze these LP roundings is by comparing our final solution to the fractional solution. So if we're forced by this nature of the polytope to lose a factor of 3, then we clearly cannot prove a better approximation factor than 3 if all we're doing is looking at the fractional optimum. Yes?
So this integrality gap is a factor and not an absolute?
Correct. In general, as we've seen, we talk about relative approximations, and for the same reason, we generally talk about integrality gaps as a ratio between the fractional integral solutions, because usually these LPs can be scaled so that it's ratios that are invariant under the scaling. Okay. And so the question is, what is the integrality gap of the stable set polytope? And it is 2. Which is to say, there are graphs for which, when you build their polytope and you look at the optimum fractional solution, you get something which is only half of the optimum integral solution. So LP rounding will not beat 2 using the stable set polytope. And in fact, Nemhauser and Trotter, many decades ago, who sort of studied this polytope, they proved something really kind of amazing, that if you look at the vertices of this polytope, okay, those vertices are all half integral. That is, at a vertex of the polytope, every coordinate is either 0, 1, or a half. And even more, if they are the coordinates that are integers, they are actually correct for the optimum. So when you solve this linear program and you get your vertex and the answers are 0, 1, or a half, any vertex that has a 1, any graph vertex that has a 1 in its variable belongs in the optimum independence, in the optimum vertex cover. Any vertex that has a 0 should not be in the optimum vertex cover. The problem is that a bunch of the vertices will have a value of a half, exactly a half, and those you don't know whether they should be in the optimum vertex cover or not. So you can do the right thing with the integer values, which gets rid of a whole bunch of the edges. It covers a whole bunch of the edges in your graph. What you're left with is a graph where the optimum solution is a half on every vertex. Okay? That's the optimum of the LP. In other words, the LP is telling you nothing at all about that set of vertices. And your rounding algorithm is just going to take all of those vertices into the vertex cover and is therefore going to be off from the fractional optimum by a factor of exactly 2. Yes?
Could you give an example of a half vertex in a graph?
I think what you're asking is, can I give an example of a graph where the optimum is to put a half on every vertex? Yes? And certainly I can give you those sorts of examples. For example, this. Right? Now, this is a graph where there is a solution where the optimum, whose value puts a half on every vertex. Now, in this graph, it's not the only solution, right? There is also an integral solution. And I don't think I can, off the bat, give you a graph where the only optimum is a half on every vertex. Yes?
Will the all cycles have half on each vertex in the only solution?
An odd cycle, would it be a half on each vertex? You could make it, let's see, so like a triangle, for example. That's going to be 3 halves, right? If I put a half on every vertex, but the optimum solution requires 2. So the integrality gap isn't 2 there. Now, if I take the cycle bigger and bigger, then I'm going to sort of head towards a solution that converges towards 2, but it's never actually going to get there. Okay.
Because we're talking about vertex cover.
Well, no, in an odd cycle, you basically have to take every other vertex, right, in order to cover. But you also have to take one extra because the cycle is odd, right? If it's an even cycle, you take literally every other vertex. But for an odd cycle, there's a little bit of wastage. Okay. All right, so that's just a little side note regarding vertex cover. What I really wanted to do today was look at some more sophisticated LP relaxations and roundings. Okay? So we're going to spend a bunch of today's lecture on the facility location problem. And this is a problem which is about like opening boba tea stands, right? Like if you open a boba stand anywhere at MIT, then suddenly it's a place where students can come to get their boba, right? And it kind of makes sense to open it near the dorm so that the students don't have to travel too far in order to get their boba, right? But if you put one in every single dorm, well, that's a lot of space, a lot of money to open up all of these facilities, right? So there are these sort of two separate things that you're looking to optimize. You'd kind of like to not spend too much money opening up all of these different locations, but you also don't want to force students to travel really far to get their infusions, right? So facility location sort of formalizes this and tries to come up with optimum solutions. What you have is a set of candidate facilities. With opening costs and you have a set of customers with travel costs. Is that what I call them? Or assignment costs. Cij, for assigning customer J to facility I. And your goal is to assign each customer to an opened facility, which of course means you have to open some of them. And your goal is to minimize the opening cost plus the assignment costs. Make sense? Okay. And so really, sort of inside here is an example of what's called a bicriterion optimization problem. Right? There's two separate criteria. There's the opening cost and there's the assignment cost. And we're interested in both of them. And we're representing that interest by adding them up into a total cost. Right? We can, of course, kind of adjust the importance of one versus the other by scaling. Right? If we double all of the opening costs, it's saying we want to pay more attention to the opening and less to the assignment, and vice versa. So you can imagine different scaling factors and kind of looking at the trade-off between the cost of opening and the cost of assignment. And you get this Pareto, what's called a Pareto curve, that sort of shows the optimum trade-offs between these two parameters. But we're just going to look at it at a particular point where we've combined them by this simple process of adding up the two costs. Okay? What can we say about this problem? Well, the general version is as hard as set cover. Okay? This problem is a lot like the set cover problem, right? Where you remember we had this order log n greedy approximation algorithm. Right? Because you can sort of think of the sets as the facilities that you're opening in order to assign each element to a set, right? And so set cover is log n hard to approximate. The greedy algorithm is optimal as an approximation algorithm. Okay. However, there are many more interesting things that can be said in the metric case, where the Cij satisfy the triangle inequality. And of course, this is what you get if you're actually talking about physical locations and straight line distances between them, which is the special case of a Euclidean metric. All right? Yes?
What does it mean here exactly to satisfy the triangle inequality? Because
CIJs, right? Right? So basically, you can imagine that the customers are in locations and the facilities are in locations, and the distances between the customers and the facilities satisfy the triangle inequality.
So can we express it as, like, with what we've introduced so far, can we express this as a constraint? Like,
oh, absolutely. Right. We're just saying that CJK, or sorry, let me put it in. So we draw a graph, right? So here we have customer I1, I and I prime. Right, and here and I double prime, right? And here we have, sorry, these should be J's. J prime, J double prime. And here we have some facility I, right? And here we have some facility I prime. And so we can now draw this graph, right, of the connections between all of the different things. And we're saying that those have to satisfy the triangle inequality. Okay? Yes?
Just make sure I understand, right? What we're trying to devise is the opening cost plus the cost of assigning each customer to one facility.
Exactly. Each customer has to be assigned to an open facility. So we have to pay to open that facility, and we also have to pay the cost of the assignment. Okay? So let's think about the trade-offs there, right? So in a sense, if we weren't worried about the, if we really worried about the assignment costs only, then we would open all the facilities, because that way we could assign every customer to the closest facility, right? But that would generate a lot of facility opening cost, right? Another option is to open a single facility and assign all the customers to it, but that's going to generate a tremendous amount of assignment cost for the customers who are very far away. So we're going to be looking for some middle ground. Yes?
For the triangle inequality, do you also consider distances between facilities? So there should be another variable for.
Yeah, I think that you're right. So the way that I've defined things, I've only talked about the assignment costs between from a customer to a facility. But the triangle inequality here is talking about all the distances, right? So there are also distances between pairs of customers and between pairs of facilities. And the triangle inequality applies over all of that. Okay? So essentially, all of these points, both the customers and the facilities are together in a metric space. Okay? So we're going to focus on the metric case where there is a hope of doing something because we don't have the set cover lower bound. Okay. And our approach is going to be the integer linear programming relaxation. Or rather, doing an integer linear program and then relaxing it. So let's figure out what the natural integer linear program is for the facility location problem. What sort of variables would we want to use? Yes?
First of all, we want flag variables for which locations we are going to open the facility.
Good. So we want indicator variables that tell us which locations are open, right? So Great. What other information do we need to describe a solution? Yes.
I guess like also indicators for assigning customer J to facility I.
Exactly. Okay, that describes a solution as a bunch of binary variables. Next step is the objective, or the formulation of the linear program itself. So what's the objective going to be? Yes?
To minimize yi at I plus yij plus 2 times CI.
Good. So we've got the opening costs plus the assignment costs. Yes? Question? Oh, okay, so now on to the constraints, I guess, is what you were.
So I guess we kind of say that we cannot have assignment of a customer to a facility if that facility isn't open.
Exactly.
And so we would say that the indicator for yi is always greater or equal to the indicator for xij.
Exactly, right? So if we write that xij is less than or equal to yi, right? Remember, yi is an indicator. So if yi is 0, it forces xij to 0. In other words, if the facility is closed, you can't assign to it. Okay? What other constraints do we have? Yes?
If we fix k, the sum of xij should be 1.
Exactly. So we have to assign the customer to a facility. So that tells us that the sum of xij's has to be at least 1.
For the second constraint, xij represents a site. Oh, wait, no. Oh, that makes sense. Cool. Sorry.
No problem. All right. Yes?
Why is it not equal to 1?
Well, so that's a reasonable question. If it's greater than or equal to 1, we're certainly satisfying, right? And in fact, we know that the optimal solution does satisfy that. So it's fine for us to say equal to, right? Sometimes if you don't want to have to think hard about exactly what the optimum solution does, you might be sloppy and say greater than or equal to. But in our case, there is an equality, there is an equal solution. And so we can rely on that. Okay? And then, of course, this is implicit in my calling them indicator variables. But we're saying that each of these is either 0 or 1, which, of course, in integer linear programming terms just means that they are 0 or 1. Right? And so, now, again, we have now given an integer linear program which exactly captures the facility location problem, right? Any solution to the integer linear program is a solution to facility location. The optima here are the optimum solutions to facility location. And so we have once again demonstrated, because this is an NP-hard problem, that integer linear programming is NP-hard. Right? But that's not why we did it. We did it because now we can relax the integer linear program. Right? And again, this is the whole point of LP relaxations, is that you don't have to come up with the relaxation. It's obvious once you've written down the integer linear program. The hard part is rounding it. And this is where all the work happens. Right? So how are we going to round this integer linear program? We get this fractional solution. What sort of insight can it give us about integral solutions? Yes?
We might try to, for each customer, choose, kind of round up the assignment which has the largest fractional part.
Good. So we could try and sort of pursue the ideas from vertex cover, right? That if you have a large xij, maybe you should round that to 1, right? That seems appealing, right? What could go wrong with that approach, right? Suppose I just took the largest xij from every customer and rounded that one up to 1. Yes?
Less than 1, and we can violate the constraint.
Good. So if we're going to round an xij up, we also have to round up the y, the corresponding y, right? And why could that be a problem for us? Yeah?
Because maybe that assignment was good for one customer, not for others. So
Exactly. This is what makes this much harder than vertex cover, right? So maybe each customer has actually chosen a different facility to have the largest fraction. And so if we round up just customer by customer, we're going to end up opening every facility. Okay, so this is what makes the problem hard, is this, this connection between different customers, this sort of necessary correlation of the decisions for different customers. Yeah?
And like look at the sum of like weight of all the customers that are, so the sum of the weights of each customer to that location.
Good. So we can start aggregating, right? And say, well, maybe what we should do is look at a facility that has a lot of customer demand, right? And open up that facility. But now we have to worry a little bit. Maybe all the customer demand is very diffuse. Like maybe all of the customers are just like spreading their demand over all the different facilities, and no one facility is getting a ton of demand at all, and so we don't have a lot of guidance. Okay, so these are things that we have to think about as we come up with the solution. The solution is relatively sophisticated, so I won't ask us to sort of invent it from scratch. The solution that we develop is going to have 2 steps. The first of these steps is what we call a filtering step, where we're going to sort of rule out the stuff that is clearly a bad idea. Okay? So we know, or sorry, it is intuitive that we are going to want to assign each customer to some facility where xij is positive, right? I mean, if we're taking the guidance from the linear program, right, having a 0 assignment is kind of saying, don't do that one, right? So presumably we're going to be looking at a positive xij. But which ones kind of does it make sense to do? Well, consider the overall assignment cost for a particular customer. Okay? This is what's known as the fractional assignment cost. All right? In a sense, this is what the linear program thinks it costs to take care of this customer. So we're going to try to use that as a guideline for what our integer solution does. Right? So we take these hints about how much should be spent assigning every customer, and we use that in our integer solution. Okay? And in particular, what we're going to say is, this sort of bounds what facilities we're willing to assign this customer to. Okay? We are going to not assign them to anything that is very expensive compared to this fractional assignment cost. Okay? So we are going to use only facilities I such that the assignment cost is less than some constant times the fractional cost. Okay? So this is where this is the first sort of approximation step. We're not going to demand that we achieve exactly the fractional assignment cost. We're going to tolerate some approximation factor in it, but we're not going to allow it to be arbitrarily far off. Okay. Now, notice that in my fractional cost, some of it may be contributed by a huge cost, which is used by only a small fraction of the assignment. Right? And so if we chose that facility, we would be spending far more than the fractional assignment cost. And so that's what we don't want to do. Okay. But here's a question. Do we know that there are facilities that don't cost a lot more than the average? Could we have a situation where all of the actual assignment costs are above average? Yeah?
Since the Xij sum to 1, you're sort of doing like a weighted average over the cost.
Exactly, right? This is a convex combination of the costs, right? This is a weighted average of the costs. And therefore, some of the costs in the weighted average can't be above average, right? This is not Lake Wobegon. So in fact, and this is actually just another way of stating Markov's inequality, right? At most, a 1 over rho fraction of the assignment weight can be greater than rho times the average assignment cost. Okay? Because, right, just this 1 over rho fraction by itself contributes 1 over rho times rho Cj. So if it were bigger than this, we'd already have a fractional assignment bigger than Cj. Okay? So we are going to discard these assignments. Okay. They're too expensive. Okay. Now, once we've done that, right, once we've discarded these assignments, we are no longer feasible. Right? We no longer satisfy that the sum of xij's is equal to 1. But we can fix that, right? We'll just scale up all of the xij's by a 1 over rho, or by a rho factor. Sorry. 1 over 1 minus 1 over rho. Right? After we discard a 1 over rho fraction, it means that at least a 1 minus 1 over rho fraction is still left. So if we scale up by this factor, we've turned the xij's back. The sum of the xij's is now bigger than 1 again. Right? But of course, in order to scale up the xij's, we also have to scale up the yi's by the same factor, so that we can be feasible on the xij less than or equal to yi constraint. Okay. So that was the filtering step. It got rid of the overly expensive assignments. Okay. And the result is that now any assignment, any non-zero assignment, corresponds to a cost that's at most rho times the fractional cost in the optimum. So that's really saying we can assign to anything non-zero at this point, and we're still going to be pretty close to the optimum. Okay. Any questions? All right. Let's talk about the opening step. How we decide which yi's to open. Okay, so now we're going to sort of use the idea that you started talking about, right? So we have all of these, in our fractional solution, we may have each facility only opening a little bit, right? And that seems like a bit of a problem, because when we take one of these only slightly open facilities and open it a lot, we're dramatically increasing that one bit of assignment cost, or of opening cost, right? So how do we pay for that? Or how do we keep that sort of comparable to the fractional optimum? Okay? And the answer is we're going to cluster the facilities together, right? So in case all of the facilities have only a slight amount of opening, we're going to find a bunch of facilities that are near each other, and in total, add up to one being open. And then we'll open one of them. Okay? So we're going to find a cluster of facilities such that the sum of the yi's is at least 1. And then we will open the cheapest one. Okay. Now, if we open the cheapest facility in a cluster, I claim we can relate that to the optimum, right? What's the relationship? Well, the point is that F min, the cheapest facility, is less than or equal to the sum of Fi times Yi, right? So this is our cost, and this is the fractional optimum, right? And therefore, we can still bound what we're doing against the optimum solution. Okay? Because we're going to open this minimum facility, but not any of the others. So we're basically taking all of the opening costs that were spread around the many different facilities, and instead, we're moving all of that opening to the cheapest facility, which only helps us in terms of opening costs. Right? Good. Actually, just to make this blatantly clear, since I skipped a step, this is at most F min times the sum of the yi's, because the y sum to at least 1, and that is less than or equal to the sum of the Fi's times yi's. All right. Now, the other thing we're going to, the reason I talk about a cluster is we're going to arrange for those facilities to be near each other. So one of them will be able to substitute for the others in terms of assignments. And that will keep the assignment cost from getting too big. Okay? So in particular, what we do is we choose the client with the minimum CJ, the cheapest client to assign. Okay? And we cluster all of his assigned or assignable facilities and open the cheapest. Okay. So that defines our cluster. Okay. Now, why is it that the sum of yi's in that cluster is at least 1? Yes?
Xij is at least 1, so the y is bigger.
Exactly. We know we have a unit of assignment. The assignment weight is always less than the opening weight on a facility by facility basis. So if we have 1 unit of assignment, we also have 1 unit of opening. Okay. Good. So we open the cheapest and we zero the others. And then we assign every customer who was assigned to any zeroed facility. Okay? So we have our particular customer J. our customer J is associated with a bunch of different facilities. These facilities are in turn associated with other customers. Right? And so the cluster of facilities is built around this particular customer. And then we pull in all of the customers who are assignable to any of those facilities. Okay. And this, of course, is where we, or sorry, I shouldn't say of course, but this is where we finally leverage the triangle inequality. Okay? Because what we're going to say is that now the cost of assigning some other J prime can be bounded by the cost of assigning it to, or sorry, let me break this down into smaller steps. So I have this, this facility J3, say, right? And according to my current fractional solution, which is feasible, right? It may be assigned, it can be assigned to various facilities. But because of the way I filtered my fractional solution, I know that any facility that it is assigned to or assignable to has an assignment cost which is bounded by its fractional assignment cost, right? So the cost of assigning, let me break it out like this. The cost of assigning J prime to the facility that we just opened is at most the cost of assigning it to some facility that it was associated with, plus the distance between that facility and the facility that we're actually opening, which can be broken out as the distance of that facility to our center, plus the distance of our center to the facility that we actually opened. Right? Now this cost, the original assignment cost for J prime, is at most rho Cj prime because of our filtering step. Right? What about this distance? Sorry, I shouldn't have, yeah. This distance is at most twice the fractional rho times the fractional distance from J, because J is only assignable to things that are that have been filtered for J. Right? So the overall cost of assigning item I prime is bounded by the sum of these quantities. Right? But remember, we took the J with the smallest Cj, right? And therefore, sorry, did I invert something here? With the smallest Cj, sorry, hold on one sec. I think I may want to take the largest Cj. Because in the end, what I'm going to argue, oh no, no, this is right. This is at most 3 rho times Cj prime, right? Because I've chosen Cj to be the smallest. So the amount that I actually pay to assign J prime is only 3 rho times its fractional assignment cost. Okay, and this is true for every vertex that I'm assigning. Sorry, there's a bad typo in my notes that threw me off. Let me fix it so I remember to fix it later. All right, and so again, we're analyzing this kind of customer by customer, and we're saying that each customer's assignment cost can be bounded by its fractional assignment, can be bounded in relation to that customer's fractional assignment cost. Okay? So that's the end of our construction. Once we've done that, right, we've opened one facility. We assign a bunch of customers. Now we can just send those. We can just get rid of all of those customers, and then we just iterate this procedure, right? Of all the customers who are left, we find the one with the smallest fractional assignment. We open a facility for them and all of their nearby customers, and we just keep doing this until every customer has been assigned. Okay. So if we combine all of this, right? We multiplied all the yi by 1 over 1 minus 1 over rho to make our new feasible filtered solution, right? And then we multiplied all the assignment costs by 3 rho, right, in this assignment step. Right? So we can balance this by setting rho equal to 4/3. Because in that case, we're multiplying everything by 4, and we end up with a 4 approximation. Okay? Which is, revolutionary. It's always been 2, and this time we got 4, which is, but of course that's only 2 squared, so we didn't really get away from 2. Exactly. All right. So that's sort of the end of the analysis, the end of the story for this facility location problem, right? We took these 2 separate steps of sort of throwing away anything which is too far deviant from what was recommended by the fractional solution. And then we used this clustering step, which relied on the metric in order to gather together little fractional pieces in order to have a full integer unit that we could open. Any questions? Yes?
Do you explain the cost of assigning j prime to I?
Yes. So this is where I'm using the triangle inequality, right? So what I'm leveraging is that I want to assign, sorry, I guess I didn't draw I in the picture. Let me put I into the picture. So there's I, right? So the question is, what can the largest cost assignment from, I'm going to assign J3 to I, and the question is, what can that cost? Right? And for that, I'm going to use the triangle inequality. I know that the cost, the distance from J3 to I is at most the sum of these 3 distances. The distance from J3 to its original assignment plus the distance of that original assignment of J3 to J itself plus the distance from J to its nearest neighbor, right? And so we break this out in pieces, right? We know that the cost of assigning J to its original assignment is at most rho times its fractional cost because of our filtering step, right? We ruled out any assignment that went too far beyond the fractional cost. So if in this picture I4 is still a candidate for J3, it means that the cost of assigning J3 to I4 is at most rho J3. Okay? So that's where we get this rho Cj prime. The other two legs are edges that correspond to plausible assignments of j, right? And again, the only allowed assignments of j are to facilities that are within distance rho cj, right? And so both of these legs are at most rho cj, and so that's where we get the 2 rho cj of the assignment, right? Now, the last argument, the last step to do this combination is simply to observe that we chose j to minimize cj. So cj is less than cj prime. And so I can replace cj by cj prime and get this upper bound of 3 rho cj prime. Good? All right. Yes?
Several times, right?
Yes, that is, we do this whole step of find the smallest cj, cluster the facilities that j is willing to use, and open one of them. Then set aside all of those facilities. They're done, right? We took exactly one of them. None of the rest are candidates anymore. And we've also taken all of the clients that would have used any of those facilities. We set all of that aside, and now we have a new, smaller problem where there are still some candidate facilities and some customers to be assigned. So we take the remaining candidate facility with the smallest CJ, we cluster facilities that it could use, and we open one of those, and we just sort of iterate this procedure until we've taken care of assigning every customer to a facility. Okay. No other questions? All right. Sorry, I'm sensing a little bit of confusion, which I'm happy to address if people can ask a question. But yes?
I think this makes sense, but the only thing I still we're not sure about is whether or not it's guaranteed to finish. Like you're not going to cancel out the assignments.
Oh, well, it is certainly guaranteed. Right, so remember, I open, I assign, and then those values are fixed. I'm never going to look at those customers or facilities ever again. That's done, right? And the point is that when I now go and pick another customer to work with, I know I'm going to get rid of that customer and any other customers that they're near. So I know I'm making progress in each of these steps. That I'm getting some of the customers assigned to an open facility. So this tells me that I will finish, right? Because there's only a finite number of customers. And I never change my mind. I never go back and say, oh, this customer was previously assigned here, and I'm going to assign it somewhere else, right? The assignment happens exactly once, and it's permanent. All right. So just a few final words about this facility location problem. One is that if you work harder, you can get it all the way down to a 1.5 approximation using some other techniques. There's also a 0.463 hardness, which of course really means a 1 over 0.463 hardness, because we know the answer is going to, the ratio is going to be bigger than 1 in your costs. This is just something that happens in approximation algorithms generally, right? So you've got maximization problems and minimization problems. And if it's a minimization problem, then what you are going to be able to do is something that is a greater than 1 multiple of the solution. If it's a maximization problem, then what you're going to do is something that is a smaller than 1 multiple of the optimum, right? And so I could give you x or 1 over x, and they both tell you the same thing about what I'm achieving, depending on whether it's a minimization problem or a maximization problem. You can sort of infer the intent. So sometimes you talk about a 2 approximation, and sometimes you talk about a half approximation, and it's clear from context which way the ratio is supposed to go. Yes?
Is it like 1 over 0.460 like greater than 1.5?
Is 1 over 0.4? Oh, that's interesting. Well, that must mean my notes are wrong somewhere. Let me see. Maybe it's 1.463 hardness. I'll check that and send a message about it or mention it next time, right? The point is that the hardness is pretty significant. It's not like one of these 1.0001 type hardnesses. But I'll check on what the exact numbers are. There are also, and some of these algorithms are based on techniques other than rounding. There's actually a very interesting approach to doing local search and like, continually improving the solution by swapping things one facility at a time, which yield these nice approximations and are more efficient than just solving a linear program. Yes? It's 1.463, okay. So let's get rid of this. Thank you very much. And that's the end of facility location. So that's great timing. Next, we've now seen this sort of use of linear programs as a way to give yourselves a relaxation without any creativity. Next, I'm going to show you how to do rounding without any creativity. So that's all that's left is having to be creative in your proof that it works. Or like I'm going to give you a rounding step that is almost always worth trying. So we'll talk about that after the break. Yes? Oh, there, yes. Fair enough, thank you. Yes? No. So if the fractional solution here has a value of 3/2, that's better than you can achieve from the integer solution. Right? The integer solution is going to have to pay 2. The fractional solution only costs you 3/2, so it's better. Oh, it is absolutely true. Like, again, because this is NP hard, there have to be cases where the fractional solution is better than the integral solution. Because otherwise, if the solution was always integral, then you would have a polynomial time algorithm. Exactly. Coming up with the examples may be complicated, but they definitely exist. Yes? Yes? Oh, I see. It should be XJI. Yeah, I think I've inherited that from the way it's always written. I don't think I don't think I get to choose, but I will check. There's a problem of being consistent with the past that sometimes gets in the way of doing what's most rational. I agree. It's set cover. Set cover is facility location with 0, 1 costs. Well, with the 0, 1 costs it is. In the general case, I don't remember. Yeah, that's what we're going to talk about next. Then you get some facility open. But you have to double check. So it's not linear, right? Because what you're going to pay is the minimum of the facilities that got opened. Right? You're not going to pay the sum of the facilities that got opened.
After the filtering step, we'll have effectively
Right, the CIJs, right? So what you pay is not the expected value, is not the sum of CIJX. It's not an expected cost of sum of CIJX, because you actually just get to use the minimum of the open facilities, so you need to double check that that still works.
fractional cost is different.
All right. Yes. So during break, I got a question, which again is really not optimal. I should get the questions during class. So I was disappointed to get asked this question during break. But what really disappointed me is that it revealed, this question got asked after class last time also, and it revealed that there are some closet complexity theorists in the class. Okay? Because now 2 of you have asked me, how do you prove the hardness of approximation? Right? And that's dangerous territory. But I will say a couple minutes about it. Okay? So you know that we prove that sort of the original theory of NP completeness worked through reductions, right? So we showed that there were lots of problems where if you could solve one, then you could solve the other one, right? And then that was this famous paper by Karp, but the really hard achievement was to show that one of these problems was hard to solve, right? And so that was the satisfiability problem. It was shown that basically any problem that could be solved in NP could be encoded as a kind of satisfiability problem, so that now if you were able to solve any of these other problems, you could also solve SAT, and that would also let you solve any other problem that could be encoded in NP. So it was the combination of having a single fundamental problem that was shown to be universal and hard, and combined with the ability to reduce all of these other problems to that one universal problem, right? And hardness of approximation has taken a sort of a similar path where, sorry, let's, I don't know if I want this to be recorded, but here I'll just write complexity. But shh. So the steps are first to develop a theory of approximation preserving reductions. Which says if I can approximate this problem to within factor A, then I can approximate this other problem to within factor B. Okay? And so I'm going to focus on constant factor approximations, but this is all more general than that. Okay? So we've created this whole network of approximation preserving reductions that says that sort of approximating any one of these problems to within a constant factor would allow you to approximate all of these other problems to within a constant factor. Okay? Now, in order to get to sort of root that in something, we need to show the hardness of one problem. Okay, you have to show one problem that is just directly hard to approximate for some reason. Okay? And that problem was the clique problem. Okay? And what they showed was that it is NP hard to distinguish between a graph that has a giant clique and a graph that has a tiny clique. Okay? And they also showed that clique could be reduced to all of these other problems. So if you could approximate any one of these other problems, then you could use that in order to distinguish between large cliques and small cliques, and that was proven to be hard. That was directly proven to be NP hard. Now, how was that proven to be NP hard? That involved a bunch of PCPs. And I don't mean that the theorists got all drugged up and thought creatively. These are what are called probabilistically checkable proofs. So you know that the theory of NP completeness, or NP hardness, is around this idea that a problem is in NP if it is easy to give a witness, right? To give a proof of the solution. Even if you can't actually come up with it's easy to check a proof of the solution. Even if it's hard to come up with the optimum solution or come up with the proof that this problem that the decision of this problem is yes or no, right? Once you've come up with that proof, it's a very easy proof to check, okay? So you come up with the proof non-deterministically, but then it's only polynomial time to actually verify that is a correct answer. So for hardness of approximation, they needed to strengthen this idea. So when you check in polynomial time a proof of solution for an NP-hard problem, you look at the entire solution, okay? People in the 90s came up with this idea of probabilistically checkable proofs, which are proofs that you can check without looking at most of the proof. Okay, so the idea here, and faculty all over the world are desperate for this, right? For the homework assignments in their class. Wouldn't it be amazing if when somebody submitted a problem set, you only had to look at the first page and decide whether that was correct? Right? We would have so much more time to watch TV if that were the case. So what was shown is that it's possible to encode the proof of a solution such that its correctness can be checked by examining only a few bits of the correctness proof. Okay. Now this is crazy, right? The key here is probabilistically checkable. Okay, and so this is related to what are known as error-correcting codes. Which some of you may be familiar with, right? Error-correcting codes provide a way of encoding information so that if any of the information gets changed, you can kind of fix up what got lost. Or, sorry, I should say error-detecting codes. There are ways to encode the message so that if it gets changed anywhere, you can see that something went wrong. You can use like checksums and things, right? And so there's a similar way to encode proofs, such that if the proof is wrong, it looks wrong just about everywhere, right? And the just about says that you pick a few random bits and you check if those random bits are correct or correct relative to each other. And if they are, then you're happy with the whole proof. And if they're not, then you declare the proof to be wrong. And there's only a small chance that you're going to miss an error in the proof once you've encoded it in this particular way. Now, this was really hard to prove because you have to worry, right? The whole idea of NP hardness is that somebody's trying to trick you, right? And so somebody could trick you with an incorrect proof, but they could also trick you with an incorrect encoding of an incorrect proof. And so you have to be robust against that kind of trickery. But people showed how to do that. So once they created this idea of these probabilistically checkable proofs, they then showed how you could encode a probabilistically checkable proof into a graph, where basically the vertices correspond to places where the proof might be inconsistent with itself, or sort of different versions of the proof. And if the proof is correct, then that graph will have a very large clique. But if the proof is not correct, then there will be no large clique in the graph. Or I may have gotten that backwards. Okay? So you can use a clique approximation algorithm to check a probabilistically checkable proof, or to determine whether there is a probabilistically checkable proof for something. Okay, so that's the sort of the series of observations is using clique approximation, I can check whether a probabilistically checkable proof exists. The vertices represent there's a vertex for each small set of bits that you might look at. And you draw an edge if those two small sets of bits are consistent with each other. Okay, and so finding a small clique kind of tells you how to make the probabilistically checkable, again, as I said, the existence or non-existence of a large clique tells you whether there is or is not a probabilistically checkable proof for this instance. And therefore, doing clique approximation lets you solve, if you could do clique approximation, you would be able to always come up with probabilistically checkable proofs, which means that you would be able to solve any NP-hard problem. So that shows that with clique approximation, you can solve any NP-hard problem, which shows you that clique approximation is NP-complete. Okay? So this is really sort of deep and beautiful work. It was actually it sort of happened while I was a graduate student at Stanford, and I attended a few meetings of the people who were trying to figure this out, but I decided it was complexity theory and I didn't want to be involved, and so I missed my chance to be part of this like awesome breakthrough that we had in theoretical computer science. Okay? So that's the story. And of course, we have plenty of complexity theory courses where you can learn all of the details of this if you are one of those closet complexity theorists. Okay. Any questions? Yes?
Why does a probabilistically checkable proof determine or allow you to solve an NP-hard problem?
It's not that it allows you. So again, the P equals NP question is basically saying if you have a procedure that can check whether a proof is valid for an instance, right? Or let's not say proof, let's say a witness. Right? If you have a procedure for checking whether a witness is valid, for instance, does that give you somehow a procedure for coming up with a witness in the first place? Right? And the same thing is here. What we've shown is that if you can distinguish between large cliques and not presence or absence of large cliques, that would allow you to come up with a probabilistically checkable proof or a probabilistically checkable a witness for any input instance of an NP-hard problem. Okay? Yes?
What do you mean by witness and instance?
Well, an instance is like, here is a graph. Does it have a small vertex cover? Okay? And a witness would be, for example, the small vertex cover. Right? But in order to check that witness, you would have to check whether all of the edges are actually covered by the vertices in your witness. And that requires looking at the entire list of vertices. So what probabilistically checkable proofs tells you is that there's a way to encode that description of the solution so that you can somehow figure out that it actually is a vertex cover without looking at the whole thing. Okay? Yeah? Well, because if you could do that, if you could come up with these probabilistically checkable proofs, that's the analog of coming up with a witness in the standard approach of showing that P is equal to NP, right? If you can develop a polynomial time algorithm that will give you the witnesses that the NP description says exist, if you can come up with those witnesses in polynomial time, then you've shown that P equals NP. Okay, and similarly here, if you can come up with probabilistically checkable proofs in polynomial time, you've shown that P is equal to NP because everything in NP has a probabilistically checkable proof.
So here you are only, you have to come up with a quick we can check whether that works.
Well, again, doing the clique approximation is essentially actually checking for the existence, right? So again, when you have an NP-hard problem, the acceptable instances are the ones for which a proof exists. So what you have to do in order to decide whether to accept a particular input is you have to decide whether a proof exists. And similarly, you can decide here whether a probabilistically checkable proof exists. And doing this clique approximation is going to tell you whether a probabilistically checkable proof exists. And a PCP only exists for the valid instances, right? So again, for the vertex cover problem, any graph that does have a small vertex cover, there is a PCP that there is a small vertex cover of that graph. So if you can show, if you're given a graph and you can answer the question of whether there is a PCP, you've answered the question of whether there's a small vertex cover. Okay. All right, so that took a little bit longer than I'd intended, because complexity theory is always about making things take longer. But I can introduce us to the next idea, which, as I said, is a way to round that you don't have to invent because it works all the time. Okay? And in order to introduce that idea, let me talk about maximum satisfiability. So satisfiability, we're all familiar with. We have these clauses, CJ, of positive and negative literals or variables, right? This is, and in the standard satisfiability problem, you want to find an assignment of true-false. Right? And in SAT, you just ask, is there a way to assign true or false to the variables so that all the clauses are true? Right? And this was the original NP complete problem. Okay. But here, we're going to loosen the requirement. There are many cases in the real world where you cannot satisfy all the constraints. So instead, you want to maximize the number of satisfied clauses. So we've turned a decision problem into an optimization problem. Okay. Now, because this is the optimization version of a decision problem, we immediately know that it's NP hard, right? Because if I could tell you what the maximum is, I would be telling you whether I can satisfy all of them at once. So we can't hope to get an exact solution. The question is, how well can we approximate the optimum? Okay. So how might we approach this problem? Any ideas for coming up with a, right? Maybe there is a great assignment. How do we satisfy a lot of clauses? Well, one pretty natural thing to try is random assignment. Okay. We've got two possible values for every variable. What if we just assign those variables at random? How many clauses are we going to satisfy? Well, we can talk about the number of clauses that we're going to satisfy in expectation. And that is going to depend on whether we satisfy a particular clause. So if we are, oh, sorry, I should have been more precise. So these clauses are ORs, right? We're using C. We're looking at the CNF problem, right? So we have an AND of ORs, okay, just like in the standard SAT that we're used to. Okay, so each clause is just an OR of a bunch of variables. What's the probability that it's satisfied? Yeah?
1 to the power of the number of variables.
Exactly. It's 1 minus 2 to the minus what I'll call k sub j, right? The number of variables in clause j. Okay. So what does that mean? Well, it means that if there are many variables in the clause, then this does great, right? As the clause grows, the probability we fail to satisfy shrinks to 0. Okay. On the other hand, if the clause only has one variable in it, we only have a 50-50 chance of getting it right. Okay. Now, an alternative, since we've just been talking about it, is an integer linear program. So how would we formulate an integer linear program for this problem? Well, it's a lot like facility location, right? What we're going to do is we're going to have a variable yi, which is an indicator for the ith literal. whether it's true or false. And we're also going to have a zj for whether clause j is satisfied. And now the objective function is pretty obvious. We want to maximize the number of satisfied clauses. And what's our constraint? Yeah.
Zj is less than or equal to the sum of the indicators.
Yeah, we have to be the only problem here is notation, right? So the constraint we're trying to capture is that a clause is only satisfied if one of the variables in it has the right value, right? But some of those variables are negated. So what I'm going to write is, let's look at all of the variables that are not negated in the clause. I'll write that as Cj plus, right? Those variables, if they're set to 1, I'm happy. On the other hand, if the variable is negated in the clause, then I need it to be set to 0 in order for me to be happy. Right? So this constraint is saying that one of the variables in the clause has to have the proper setting before I can declare that clause to be satisfied. And then again, we have the usual constraint that the xi's are between 0 and 1. Okay. So this gives me an integer linear program, which immediately gives me an LP relaxation. And again, the hard part is rounding. And so here is where we apply non-creativity. Okay, and hopefully I've kind of primed the thinking by talking about this random assignment. Notice that we've constrained all of our xi's to be 0 or between 0 and 1. So what is often between 0 and 1? A probability. So what we're going to do is we are going to think of each xi as a quantum variable, right? It is a right. So xi equal to 3/4 is now going to mean a variable that is true with probability 3/4 and false with probability 1/4. Okay. Or sorry, these are the yi's. Right. So we are going to round this problem simply by flipping coins for each of the variables, right? In order to decide on the truth assignment. And next time, I will show you how we can analyze this rounding in order to prove a good approximation ratio for MaxSat. Okay? And so next time, we're going to finish up approximation algorithms, and we're going to start our next topic, which is a little bit of fixed parameter tractability. All right? See you next time.